Okay, so we've heard a lot about kind of the history of the department as it is now, and the research that's been going on here. And for this final talk this afternoon, I'm going to talk a little bit about this Computer Architecture Research Centre, which we're launching today. It's a centre, as people have mentioned, to fund PhD students through donations to work on some of the grand challenges in the kind of computer architecture area and related sort of fields. So I'd like to start just with an overview again of the research that we've done, but taking kind of a broader look at things. And this word cloud is something I generated from the paper titles from within the group. Okay? And you can see things there that you might well recognize, words like hardware and software and so on. But what I want to sort of draw your attention to really is kind of the breadth of research that we're doing here and the kind of breadth of areas that we're covering. You know, we're looking at compilers through to circuits, we're looking at security, performance, reliability, we're looking at applications, specialized compute to actually run them efficiently and accelerate them. And this breadth of research is something that we're really proud of, and we think that it makes for better research to do kind of wide-ranging across the stack, looking at different areas. We think it's better research, and it leads to better insights and better kind of students coming out of the group as well. And, you know, to kind of cement that, I'd like to talk about some of the awards that people have won in the group, okay? Simon's already mentioned Dan Greenfield, who won the BCS Distinguished Dissertation Award with his thesis. One of Rob's students, Aaron, became an Apple Scholar. This is a very prestigious award. Apple only gives out a handful of these awards every year across the entire globe. So for Aaron to win it was a fantastic achievement. We've had papers that have won the most influential paper award in 10 years. So here's a photo of Simon receiving the prize for that at the ASPDAC conference a little while ago. ISCA, the top conference in computer architecture, turned 50 a little while ago, and they had a retrospective of work that had been published in that conference over the previous 25 years. And again, one of Simon and Rob's papers got selected for that retrospective edition of ISCA, which was very prestigious as well. And of course, we've had Best Paper Awards in various of the top conferences like this one at Micro just last September. Okay, so we're doing kind of great research, and we're winning awards for the research that we're doing as well. And that's kind of recognized, I guess, by where our students tend to go afterwards. This is some of the logos of companies and places that our students end up after they leave the group here, having kind of come out and done a PhD. And so you can see, obviously, big names like AMD, ARM, NVIDIA, and so on. We've got kind of newer companies like Sci5 there as well. We've got companies whose logos I couldn't find, like the startups that have come out of the group that have then been bought on, and people have gone on to do great things as well. And of course, our students go into academia as well, and so we've had people go into, I picked out 3 of the universities in the UK where people have gone on to become faculty members, so Edinburgh, Bristol, and Imperial. We've had other group members go overseas to join universities abroad as well. And so, you know, our students are very much in demand. They're doing great research here, and then when they leave, they get snapped up very quickly by lots of different people working in this area. And, you know, kind of recognizing that, as Alistair said, we've invested in this area as well. So last year, we appointed 6 new faculty members in the whole of the department, and 2 of those people were in the computer architecture group. Okay. So Prakash joined us from Microsoft, and Tobias joined us from Edinburgh. And I'm just going to take a moment to introduce them and for them to say a few words about their research. Okay, Prakash, if you'd like to.
Thanks. So my name is Prakash Murali. I've been here for about 6 months now. I joined in January. And before this, I spent 2 years in Microsoft, where I was part of their quantum computing program. And before that, I finished a PhD in Princeton in 2021. So I started doing quantum computing as part of my PhD, and I looked at problems in how we compile quantum programs to hardware and how we can design better quantum hardware. And I developed techniques like noise adaptive compilation, where we really wanted to take current quantum systems, which are very noisy, and see how we can adapt program executions for these devices. And similarly, look at instruction sets and quantum architecture and see how that should cater to the needs of these small programs that we can run on quantum computers now. So all of this research that I did during my PhD, really helped me understand what are big problems that we face in the field and where this field needs to go. And that's the reason why I decided to switch over from industry to academia, because I think there's a lot of long lead time research topics that we need to look at in order to really bring quantum computing to fruition. So the most important thing to look at is why do we want to build quantum computers in the first place? And the answer is that there's a lot of hype and there's a lot of interest in applying quantum to different fields, finance, predicting stock markets, predicting the weather, all sorts of things. But what we've seen in the last couple of years is that there's really a small set of applications where we can expect quantum computers to succeed and succeed in a way that it's transformative for society. And one of the big applications is tackling climate change. So if we can use quantum computers to design new catalysts that can help us, let's say, sequester carbon, that would have major transformative implications for the world. So when we want to realize applications like this, what are the kind of quantum systems that we want to build in the next 5, 10, 15 years to make these big visions happen? So that's the big question that my research asks. That is, how can we co-design the hardware and the systems, the software and the architecture to really enable these systems to succeed in the next decade or two? And towards this, I think of this as a bunch of milestones that we need to get to. So we currently have noisy quantum computers with about 50 to 1,000 qubits. They're good for doing small demonstrations, but we can't really do very useful computations on these devices. And what we want to get to is very reliable quantum systems with upwards of 1 million qubits to tackle big applications. So as part of my research, what I plan to look at is to first understand how can you build error correction on these noisy quantum systems to make them much more reliable. So how do we co-design quantum error correction and the hardware that we're building in the next 5, 10 years? And as I started looking at this, one thing that we've realized is that monolithic quantum computers are not going to scale. So if you build single quantum devices, one chip, that is not going to scale. And this is fairly obvious to people who have been in computer systems, but not so obvious in physics and other communities. So the second thing that I want to look at is what is the kind of architecture that we need when we want to have quantum computation that is distributed across multiple nodes. And the last thing is, we know for sure that applications in chemistry are going to be really important, and this was the reason for the inception of the field itself. So I want to look at how can we design quantum computers specifically tailored to these domains. So to see how we can use properties of these applications and tailor the software, the instruction sets, the microarchitecture, and the qubit itself to make these applications happen sooner. So it's a really exciting time for me as a faculty, and I would love to talk more about potential overlaps and opportunities to work together on these topics. Thanks.
Excellent. So I just realized I'm here already 8 months, just a couple of months before Prakash I joined. And you have already heard a lot about some of the research I'm doing. So B shared with you what we want to do in the circuit space and the hardware design space. And in some way, I'd just like to continue that presentation, right? So B said, there is an opportunity in the hardware design space to take the lessons that we took in LVM in the software space and scale up or transmit these ideas to the hardware space, right? And so then I'm wondering, where else can we put these lessons to fruit? Where else can we really build larger scale compiler style systems, right? And so in a way, I'm personally interested in particular in contributing to how we build AI compilers, how we build compilers for embedded systems, for quantum computed climate change, meaning pretty much any kind of HPC style system. And that sounds a little bit unfocused, right? I just want to build compilers wherever I can. And that somehow makes sense, right? But there's a reason for being unfocused, right? And I think that historically we kind of understood that a compiler is the C++ compiler. This closely knit community of people who understand how to translate C++ code to assembly code. And in some way it's a handcrafted product. Really well built for that specific domain. But then again, what we see in the hardware design world, we need to do it once again, right? And MLI is a really cool tool because it says, actually, you don't need to do everything once again. And my question is, can we scale that further, right? And so one direction that we just partially mentioned is, but which is mentioned here nicely on the slide, can we use formal verification tools, both as an opportunity to actually build LVM, MLIR style compiler technology into the underlying functional programming languages, that they benefit from a really large compilation stack, very powerful compilation stack, but also, and I think even more importantly, is there a way to use these formal verification tools, in particular tools for program synthesis and automatic verification of parts of a compiler, to accelerate the growth of the compiler ecosystem, right? If we have a hardware compiler like Circuit, if we have a software compiler like LVM, if we have compilers for AI, all of these compilers today are mostly handcrafted, and I think there's a big opportunity to increase the degree of automation, the degree of tooling that we can have, to empower our developers, to empower compiler developers to be a lot more productive in building these compilers, right? And that kind of connects a little bit back to the story that Rob was sharing at the beginning. If we want, and actually what Renato said earlier, if we want to adapt the software stack on top of all the rapidly changing hardware, we can't really continue to handcraft our compilers for the next 20, 30 years, right? And in some way, I guess that's what we as a research group do. One of the things that I'd like to point out in particular, which I find, I think it's important to point that out in a venue where we are really all like technical experts, but I think most of you will have realized that being a technical expert is really not the one thing that like made you succeed in your career or in your mission, right? The second thing you typically need is to really understand how to work with your peers, your colleagues, and in the open source community, really how you work with a large-scale, globally distributed community. And I think that was one of the reasons why I was really excited to come to Cambridge, to see several examples of where we had an idea, and then kind of the people here in Cambridge went a little bit out of control and implemented that idea at scale, globally, open. And I think that's some of the research that we in our research group also strive to deploy is not just doing a research project, but doing a project, delivering it in a large-scale open source community, and kind of deploying it maybe to production. So maybe some of your cell phones have some of our compiler code on your cell phones. And yeah, some of the research we are doing that benefits from working really closely with industry on large open codes, but also allow our students benefit because they can see their work actually end up being deployed quite quickly. So I'm actually really happy, like one of our research projects that we launched like 3 or 4 years ago where we wanted to build a fast library for linear algebra or constraint programming. It took us roughly 1 or 2 years to build it up in the MLIR compiler stack. And I think just a week ago, some engineer I didn't know from a company here in the UK posted a message and said, yeah, this would be really useful to have an LVM. Would anybody mind me moving it over? And I was really, I wanted to say, yes, that's what I want. And I was just like, no, Toby sat down, watched, relax, and without a single message of myself, actually, some of my students got involved, and actually several other people from the community. Now that code base is moved into LVM. Apple will use it for like some of the constraint analysis that they implemented in LVM. So this was one of the like small stories I wanted to kind of end with on my slide. I really like if we do research, we deploy it, and then someone else moves it forward somewhere into the community and actually builds something around it. Thank you so much for attending.
Okay, so you can see, as I said, we've invested in this area. We've got 2 new faculty members here, and Tobias and Prakash have strengthened the research that we can do and also broadened it even further than what we had before. And I wanted to take a step back now and look at the kind of picture nationally. So this is the National Semiconductor Strategy. Like all government publications, obviously essential bedtime reading. I'm sure you've all looked at it in great detail. It kind of lays out how the UK is, the state of the world, the UK in semiconductors, and it sort of lays out the fact that we've got, fantastic design and IP kind of computer architecture environment in the UK, which is obviously great. It also mentions Cambridge here in the Digital Security by Design Challenge that Simon mentioned as well, that directly comes out of the Cherry work. And so, in some ways, the picture is quite rosy, and it's great. But it also sort of sends a warning out, right? And it says we need more investment in the area, and in particular, in people. Okay, so I just picked out a few quotes from it. It says, from our engagement with industry, it's clear that the UK needs to do more to sustain and grow the pipeline of talent available. There's a clear demand for skilled people to work in the sector. And the semiconductor industry relies on a supply of strong intellectual talent who tend to be at postgraduate level. So, there's kind of 3 things going on here in many ways. We're doing fantastic research here in Cambridge and producing really, really good PhD students who are going out and doing great things. At the same time, we've kind of got the National Semiconductor Strategy saying that we need investment in this area. We need to train more people. And the third thing, of course, is the department is investing in this area already by appointing 2 new faculty members, increasing our capacity to actually train students and send them out. And that's why, we're launching today this Computer Architecture Research Centre. Okay? It's a research centre to fund PhD students. It's okay. It's technology, it's a pain, isn't it? So, the PhD, it's a Computer Architecture Research Centre is a centre to fund PhD students through donation, okay, so that we can continue doing the kind of world-leading research that we're really good at so far. And I have to say, if we're going to be designing chips like that, then I'm thinking of doing a PhD all over again, because this looks fantastic, right? So what we're going to be doing is aiming to have a cohort of 6 to 8 students every single year starting their PhDs, and every sort of 6 months or so we'll have showcase events where the students get together to interact with people, to share their research and have a conversation about their research with the wider world, with everyone here, I hope, who will interact with us then as well. It's going to be driven, with a strong academic kind of focus, but we also want input from industry as well to tell us where you think the challenges in the area lie. I mean, we have our own ideas, I'm sure you're aware of that, but it's interesting for us to get an industry perspective on the work as well, and I hope that the talks that we've had today show you the value of our interactions with industry and why that makes, the kind of partnership between academia and industry makes the research even better and kind of meets the challenges. And so we'll also have roundtable discussions once a year for us to present our vision to you, but for you to kind of talk to us about where you see the challenges and the pinch points lying and what you think should be the upcoming things that we look at. We're going to be, as I said, looking at some of the grand challenges in the area. We haven't 100% defined everything, but I've picked out kind of 2 areas that would probably be of interest, I think, to the audience here. So the first one is sustainability, which I think is a really key challenge. I thought this audience might appreciate a strapline like doing more for less. Sorry. But actually, I don't think that kind of covers it enough, because energy efficiency is only kind of one of the areas that I think we need to cover when we're looking at sustainability. And we need to look at the whole environment in which we're doing research here. So I've actually kind of picked out the mantra of reduce, reuse, and recycle instead. Okay? So the green arrows on the left are reduce. They are, we need to be doing the compute with less energy so that we're burning less power. We don't have so much resource requirements from our chips when they're operating. But also, I think it's also about thinking about those chips themselves and not creating chips that are too big for the task that's required. Right? The chips that we design and we build are hugely expensive, but they're also hugely energy intensive to actually create them. And so when you have a chip that's being produced, there's a lot of embodied kind of carbon inside it. And so we have a responsibility, I think, to try and minimize that as much as possible and build chips that are as small as possible to do the tasks that we've got at hand. Okay? The reuse in the middle, of course, is that we want to use as much of the chip as possible. As soon as we're underutilizing the chip, then that's kind of a wasted resource, and all that energy that's gone into manufacturing it isn't being used in the way that it could be. And so we want to get the maximum performance out of it. We want to, say, build specialized accelerators for different workloads or different parts of our workloads so that we can be as energy efficient as possible when we're computing. But then we need to allow a certain amount of flexibility in that to tailor them to kind of other problems that they weren't necessarily explicitly designed for, so that we get utilization out of them whenever we possibly can. And the recycle on the right-hand side really kind of considers the fact that there's going to be more errors occurring. Reliability is a major concern, and we don't want to just throw away chips as soon as they kind of, transistors wear out and we get hard errors occurring. We're very used to dealing with soft errors, transient errors in certain scenarios. We need to be better at dealing with hard errors as well, and keeping computation going to extend the life cycle of our chips as long as possible. So, computing with errors, there's a whole field of approximate computing which allows errors to creep in, which is absolutely fine in certain workloads. But there's other things that we can do as well to keep processors, keep the cores that have got errors in them doing useful work, perhaps to produce results that predict what's going to happen to another core in the system, if you can do it in an efficient way. And, these things are kind of in tension with each other at times, right? We're going to want to keep things working as long as possible, but then it's going to use more energy by doing that. And so we have to find trade-offs and things to balance this out and really make the systems as sustainable as we possibly can in the longer run. The second area I couldn't really not mention either was what I call ML for systems and systems for ML. And Rob's already talked a bit about this, as has Carl. On the left-hand side there, we have our ML for systems. And that's really thinking about the fact that, our chips do contain a lot of predictors, a lot of machine learning models go into our modern cores, our modern high-performance cores. And we can do better about designing those cores. We can do better about embedding the machine learning so that we do prediction better, as was the purpose of Carl's talk really today. And on the right-hand side, of course, we've got systems for ML, recognizing that machine learning workloads are hugely important and they're not going to go away anytime soon. And we want to build, obviously, cores that can be as efficient as possible when running machine learning workloads, cores that run machine learning workloads in different scenarios, so not just in the data center, but at the edge as well. And how can we obviously build systems that meet this challenge, perhaps alongside the sustainability challenge that I outlined earlier. So just to conclude then, we're launching this Computer Architecture Research Center. We're hoping to fund PhD students who are going to do some great research looking at all the grand challenges in the area. I hope what today has brought is the start of a kind of dialogue and a conversation with you and the wider world about what the challenges are and how we're going to meet them. And I'd love to talk to you more about it afterwards. Thank you very much, and if you've got any questions, then please let me know.